In the last session, we had a discussion about the concept of transactions. We have seen what we mean by transaction. We have gone through the important properties of the transaction, and those are known as acid properties. So every transaction in the system must satisfy these properties. So A stands for atomicity, C stands for consistency, I stands for isolation, and D stands for durability. Later, we had a discussion about the state transition diagram of a transaction. So what are the states in which a transaction may enter? So we have gone through all those steps. And finally, we discussed about the SQL statements commit and rollback with respect to executing the transactions. So today we are going to discuss about concurrency control. So let's proceed with few important points related to concurrent execution of transactions. So in modern database management systems, multiple transactions are allowed to run concurrently in the system. So it is not the case that only one transaction is present and running at a time in the system. It may happen that several transactions are concurrently executing in our system. So what are the advantages actually that we have of this concurrent execution of the transactions? So the very first advantage is we can observe increased processor and disk utilization because of concurrent execution. What we mean by that? A transaction actually consists of many important steps or operations. So some of the operations involve some kind of input-output related activities, read-write operations, or some operations involve the CPU activity. So the CPU and the disks can operate in parallel. Therefore, I/O activity can be done in parallel with processing at the CPU. So we can achieve some kind of parallelism here of our CPU and the I/O system. So this parallelism of CPU and I/O system can be exploited to run multiple transactions in parallel. So while one of the transaction is busy in reading or writing some data onto the disk, another transaction may utilize the CPU time. So these two transactions can run concurrently. One is using some I/O operation and other is using CPU time. While it may happen that if we are having more than one disk, one transaction might be carrying out I/O operations with respect to one disk. One transaction may be carrying out I/O operation with another disk. Another transaction, third transaction may be executing some instructions and using the CPU time. So it may happen. So all these kinds of activities and the parallelism that we may have in I/O system and CPU utilization, this all increases the throughput of our system. So what we mean by throughput of our system? Meaning the number of transactions those are executed in a given amount of time. So what is transaction throughput? It is the number of transactions those can be executed in a given amount of time. So correspondingly, the processor and the disk utilization can also increase. So by having the concurrent execution of the transactions, it is possible to increase the processor and disk utilization. Right? So this is the very first advantage of having concurrent execution of our transactions. Second advantage we may have is the reduced average response time for transactions. So what we mean by that? Usually it happens that there is a mix of transactions running in a particular system. So few of the transactions are short, whereas few transactions are very long. So if we allow transactions to run serially, what will happen? A short transaction may have to wait for a preceding long transaction to complete, right? And this may lead to some kinds of unpredictable delays in running the transactions, right? But if we are allowing the concurrency in the system, then it may happen that these short transactions need not wait for the longer ones. So they can be executed at a time. They can be executed concurrently. So obviously, this concurrent execution reduces the average response time. What we mean by average response time? The average time for a transaction to be completed after it has been submitted to the system. So as it is possible now that the transaction need not to wait for some longer transactions, obviously there is reduction in average response time. That means once the transaction is being submitted to the system, right, and the time that it gets completed, this time of completing the transaction, the average time, that gets reduced. So these two are the important advantages why we should have the concurrency in our system. Now, if we would like to have concurrent execution of transactions, then we should have some mechanism that will control such kind of concurrent execution of the transactions. So the coordination of the simultaneous execution of transaction in a multiprocessing database system is known as concurrency control. So somehow in database management system, the system needs to coordinate the simultaneous or concurrent execution of the transactions. So this mechanism or this process of coordinating the simultaneous execution of transactions is known as concurrency control. So if we are having concurrent execution of transactions, there are certain potential problems, those we can observe, right? So what are those problems? So we have listed here three important problems, and these three problems are the lost update problem, or it is also known as multiple update problem. The second problem that we may face is the uncommitted data problem, and the third problem is the inconsistent retrievals or incorrect analysis problem. So if we are allowing the transactions to execute concurrently, then obviously such kinds of problems may occur. And we need to build a mechanism that will solve these problems. So let us go through these problems one by one and let us understand what we mean by these problems. So let us see first the lost update problem or the multiple update problem. So I'm going to demonstrate this problem with one example. So let us assume that we are having one account, say account A, and the initial balance of this account is say 1000 rupees, right? And we are having two transactions, transaction T1 and we are having transaction T2. So what this transaction T1 is doing? This transaction is withdrawing amount 50 from account A, right? So transaction T1 is simply withdrawing amount 50 from account A, whereas this transaction T2 is depositing amount 100 in account A. So both the transactions are dealing with the same account, account A. So the first transaction is withdrawing the amount and the second transaction is depositing the amount. Right? Now, if there is a normal execution of T1 and T2, meaning the serial execution of T1 and T2, then what would be the ultimate balance of account A? So see here, what we mean by serial execution. Serial execution means transaction T1 is executed completely and then T2 starts, right? So if I'm executing this transaction T1, I'm having 3 operations to perform under T1 and also I'm having 3 operations to be performed under T2. So what T1 is doing? T1 is withdrawing the amount 50 from account A. So T1 needs to read the initial balance of account A. So as we mentioned, the initial balance of account A is 1000, right? So T1 is reading that amount and then T1 is withdrawing that amount. Withdrawing means we need to deduct amount 50 from that balance. So T1 is executing the statement like A gets updated now as A equal to A minus 50. So we are withdrawing 50, right? So after this operation, what next T1 needs to do is T1 needs to write the balance amount back to account A. So T1 is executing the statement write A. So obviously now this T1 is writing this amount 950. So after executing this transaction T1, we are having balance of account A as 950. Right? Now, after completing this T1, T2 comes in because there is serial execution. So whenever T2 comes in, then T2 is now reading the balance A. So which balance T2 is reading now? Whatever has been written by this T1. So T2 is reading now this balance 950. T2 is depositing amount 100 in account A. So T2 is now executing this operation. So A gets updated such that A is equal to A plus 100 because it is deposit, right? So the balance of A would be increased by 100. And finally, T2 is writing this balance amount into A's account. So obviously, the T2 is writing now the amount 1050 in A's account. So final balance after execution of T1 and T2 is 1050, right? So this is the way how our transactions T1 and T2 are executing in serial fashion. It may happen that the another order of serial execution is first T2 gets executed and then T1 gets executed, right? So both the serial orders, either T1 then T2 or T2 then T1 are allowed under this kind of normal or serial execution of transactions T1 and T2, right? So this is how the serial execution works. Now we are talking about the concurrent execution of transactions, right? So let us see now how these two T1 and T2 will work concurrently, right? So we are having once again the initial balance of account A as 1000 and the same transactions T1 and T2 we are having. So T1 is withdrawing amount 50 and T2 is depositing amount 100 in account A. Now we are having this form of concurrent execution of T1 and T2. So see here, the instructions from T1 and T2 are interleaved. So it is not the case that T1 gets executed first and then T2 starts. Instead, we are having here the first instruction of T1 that gets executed, then the first instruction of T2 that gets executed, and so on. So see here, in this scenario, what is happening? This is concurrent execution, one way of concurrent execution, wherein T1 is first reading the balance A. So T1 is reading the balance as 1000. Now the next instruction that is executed is from T2. So T2 is also reading this balance of account A. So once again, T2 is reading the same balance, that is 1000. Now comes the instruction from T1. So see here, T1 is withdrawing 50. So T1 is executing A equal to A minus 50. So this instruction gets executed. Next, once again, the instruction from T1 gets executed. So T1 is writing the amount A. So obviously, T1 has read 1000. T1 has subtracted 50 now from A. So the value of A becomes 950 and the same value is written by T1 into the database. Okay, now T2 has not yet completed. So T2, the next instruction from T2 is being executed. So T2 is depositing 100. So A gets incremented by 100. So T2 has seen this value 1000. T2 has read this value 1000. So obviously T2 is incrementing this 1000 by 100. So now A becomes 1100, right? And T2 is now writing 1100 onto the database. Correct? So if we look at this sequence of instructions, what has happened? This value that was written by T1 was lost. Why? Because after T1 has written this, T2 completes its working and T2 is overwriting this value 950. So ultimately at the end we are getting the balance as 1100. And actually what is expected? We are expecting the balance that was earlier we have seen 1050, because always serial execution of transaction always is correct. So ultimately what is expected after these two transactions is the balance 1050. But if we are following concurrent execution of T1 and T2, which is uncontrolled right now, okay, and if we allow such kinds of steps while concurrently executing these two transactions, then what has happened here is whatever the value written by T1, that is 950, was lost. So this problem is known as lost update problem. T1 has updated the value, but after that T2 has written the value, and that is why this value yes or no? This problem is we have lost one of the updates that was carried out by T1, or we may say that there is a multiple update problem, right? So the same account has been updated multiple times, and that is why one of the update was lost, right? So if these two transactions T1 and T2 are concurrently executed in a wrong way, then we may face this problem of lost update, right? So let us go to the second problem, and that second problem with concurrent execution of transactions is the uncommitted data problem. So what we mean by that, uncommitted data problem? So this problem occurs when one transaction can see the intermediate result of another transaction before the first transaction has committed. So what we mean by that? Let us assume once again that T1 and T2 are executing serially, right? And what are my transactions T1 and T2? See here, transaction T1, once again the same transactions T1 and T2. So T1 is withdrawing 50 and T2 is depositing 100 in same account A. But what has happened? See here, this is the correct execution actually of T1 and T2. So T1 has performed till this, right A. So T1 has written the value of A, right, after withdrawing amount 50. So T1 has written this 950 in account A. But what has happened? Due to some problem, there is a failure, right? And due to that, this T1 has rolled back. See here, we are having this step roll back. What we mean by this rollback? Due to some failure, T1 has not completed successfully, and that is why T1 has rolled back. Meaning, whatever are the updates, those are performed by T1, those will get nullified. So, even though this was written earlier by T1, due to this rollback statement, what will happen? The entire thing gets reversed. So once again, after T1 gets rolled back, what we will be having is, we will be having this value 1000 back, which is the balance, initial balance of account A. Let us proceed now with this transaction T2. So T1 has rolled back. So once again, our account balance A is 1000. And now T2 proceeds with its working. So T2 is reading 1000, T2 is incrementing 100, depositing 100, and after depositing it, it is writing back the last balance, final balance to the account A. So it is updating A's balance as 1100. So obviously, this is the correct execution of these two transactions T1 and T2. Right? Now, let us see the other way of execution. Right? So, as I stated, this uncommitted data problem occurs when one transaction can see intermediate results of another transaction before it commits. Right? So, now let us assume that T1 and T2 are executing concurrently. So T1 rolled back after T2 accessed the uncommitted data. What does this mean? See here, this execution. So what we have here is, see, T1 is reading the balance of A, so 1000. T1 is withdrawing 50. T1 is writing this amount to A's account. So T1 is writing this 950. Okay. T1 has not yet committed, or even T1 has not rolled back, right? But my system is allowing T2 to read this uncommitted balance, this uncommitted data. T1 has written A, but this value is uncommitted. What we mean by uncommitted? T1 has not yet committed, or T1 has not yet rolled back. So this intermediate value 950 is read by this another transaction T2, right? So T2 is reading now this 950 and T2 is now depositing 100 into this balance. Okay, so T2 is depositing 100 into this balance. So obviously T2 will have the balance as 1050. So after this statement, my T1 gets rolled back. So there is some problem with T1 and T1 gets rolled back. So if this statement is encountered at this place after T2 has read whatever is written by T1 and now T1 is being rolled back. So what will happen? Rollbacking of T1 means what? All the updates, those were performed, will be rolled back. So T1 will once again produce the A's balance as 1000. Right? And now T2 is writing A. So T2 has computed A's value as 1050. So T2 is writing this A. So T2 is writing 1050. But now please see here, as T1 has rolled back, this T1 needs to be nullified, right? And T2 only is valid. And ultimately, the expected value is 1100 because only T2 has successfully come. But what has happened? The value that is being stored in the database is not 1100, but it is 10. And why it has happened? Because whatever T2 has read, that was the data that was uncommitted by T1. Right? And said the uncommitted, and that is why ultimate result of these two transactions collectively is wrong. Right? So once again, in this kind of uncontrolled situation, if two transactions T1 and T2 are concurrently executing, then another problem that we may face is the uncommitted data problem. And this problem occurs when one transaction can see the intermediate results of another transaction. Right? So T2 is reading this intermediate result of transaction T1 before T1 commits. Right? And that is why the wrong value has been read by T2. So ultimately, the wrong result is being produced. Right? Are you with me? Any doubt so far? Yes?
No doubt, ma'am.
No doubt. So may I proceed?
Yes, ma'am.
Right. So let us go to the third problem that we have listed. And this third problem is inconsistent retrievals or incorrect analysis. Right? So this problem occurs when a transaction calculates some kind of summary or aggregation over the set of data, while the other transaction are updating the same data. What we mean by that? Let us assume that we are having two transactions T1 and T2. So what T1 is doing? T1 is calculating the total of account balances. So let us assume that in my database, I am having 100 accounts. Right? I am having 100 accounts. So what T1 is doing? T1 is summing up all the balances of these 100 accounts. Right? So what my T1 is doing? My T1 is summing up the account balances. So I'm having 100 accounts. So all those 100 accounts are having 100 different balances. So transaction T1 is simply computing the sum of balances. And what my transaction T2 is doing? My T2 is updating the balance of some accounts. So T2 is updating the balance of two accounts, say account A and account B, right? So transaction T1 is summing up the balances including A and B, and at the same time T2 is updating those balances of accounts A and B. So obviously one transaction is performing some aggregation function over all the data, while other transaction is updating few of the accounts from the same data or updating the same data, right? So obviously, as a result of execution of these two transactions, obviously we are getting some undesirable results, right? So this problem is known as inconsistent retrievals, or it is also known as incorrect analysis. And this occurs when one transaction is carrying out some kind of aggregation function and other transaction is actually updating the same data. Right? So this is the third problem that we may have while executing our transactions concurrently. So we have listed three problems. What was the first problem? That was the lost update problem or multiple update problem. What was the second problem? Second problem was uncommitted data problem. So this problem occurs when one transaction can see intermediate results of another transaction before the transaction commits, right? And the third problem that we discussed was the inconsistent retrievals or incorrect analysis problem, right? So while executing our transactions concurrently, we may face these kinds of problems, right? So let's proceed now with the concurrency control schemes. So we have seen why we should have concurrent execution of transactions. So what are the advantages of concurrently executing the transactions? And if we want to have those advantages of concurrent execution, then we should allow our transactions to execute concurrently. But if we are not controlling those transactions while concurrent executions, then we may face some problems. And we have gone through the problems those we may face in case of concurrent execution. So, to avoid such kinds of problems, what we need is we need to devise some mechanisms. And these mechanisms are known as concurrency control schemes. So, what we mean by concurrency control schemes? These are the mechanisms to achieve isolation. That is, to control the interaction among the concurrent transactions in order to prevent them from destroying the consistency of the database. So if we allow the transactions to perform in uncontrolled way, then we may face certain problems and those result in inconsistent database. So to avoid such kind of inconsistency in the database, we need to control the interaction among the concurrent transactions, right? And such mechanisms, those we are going to devise to achieve isolation. These mechanisms are known as concurrency control schemes, right? So let us see now what are actually the objectives of the concurrency control schemes. The first objective of concurrency control scheme is to schedule or arrange the transactions in such a way as to avoid any interference. So no doubt, we are going to allow concurrent execution of transactions. But now we are going to have some control over this concurrent execution, right? So the first objective is to schedule or to arrange the transactions in such a way as to avoid any interference, right? So one transaction need not interfere execution of other transaction. So we need to take care of that, right? And accordingly, we need to arrange the transactions. The second objective is to devise the strategies to maximize the concurrency in the system. And this is really important. Why? Because if we are maximizing the concurrency in the system, then obviously the throughput of our system will be increased, right? So the concurrency control schemes are actually need to be built or need to be developed with these two objectives. The first objective is to arrange the transactions in such a way as to avoid the interference. And secondly, we need to devise the strategies those can maximize the concurrency in the system, obviously leading to the high throughput of the system, right? Now, to come up with such kinds of concurrency control schemes, now let us focus upon few important concepts, right? So, the database management systems are having a spatial program, and that is known as a scheduler. So what is the role of the scheduler? The role of the scheduler is to create the schedules, right? So scheduler is the spatial database system program that creates or that generates the schedules. So what we mean by a schedule now? A schedule is a sequence of instructions. So sequences that indicate some chronological order in which the instructions of concurrent transactions are executed. I'll repeat, what is a schedule? So schedule is some sequence of instructions, right? Sequence of instructions from multiple transactions. Right? So this sequence is giving us some chronological order in which the instructions of concurrent transactions are executed. So there is some interleaving of instructions from concurrently executing transactions, and such kind of a chronological order is being generated by a scheduler, and this chronological order in which the instructions need to be executed is known as a schedule, right? Schedule for the set of transactions must consist of all the instructions of those transactions. So if I am having a schedule wherein say two transactions are participating, say T1 and T2, then a schedule must have all the instructions from T1 and all the instructions from T2, right? The schedule must preserve the order in which the instructions appear in each individual transaction. So what we mean by that? Suppose my transaction T1 is, say, read A, then A is equal to A minus 50 and write A. So transaction T1 is having this order of instructions. And similarly, there is some order of instructions. So schedule must preserve the order in which the instructions appear in each individual transaction. So while preparing a schedule, read A must appear first from transaction T1, then only this A equal to A minus 50, and then only this write A. So change of this order of instructions from a particular transaction is not allowed. So in a schedule, this order must remain the same, whereas schedule may interleave the instructions from T1 and T2. So I may have the combination of instructions from T1 and T2 in a schedule, but the schedule must preserve the order in which the instructions appear in individual transactions. Right? So I hope the concept is clear. Right. So the role of scheduler is to generate the schedules, ensuring serializability and isolation of transactions. So please note down this word serializability that we are going to explore further. So role of scheduler is to generate the schedules, ensuring serializability and isolation of transactions. Further, schedulers need to use the concurrency control algorithms. Those we are going to focus upon next. And also, the schedulers must ensure the efficient use of CPU. So these are the roles of scheduler. First, to generate the schedules, ensuring the concept of serializability and isolation of transactions. Secondly, the scheduler need to use the concurrency control algorithms to come up with the schedules. And third, the scheduler need to ensure the efficient use of CPU so that the throughput or high throughput can be ensured. Right? So, let us see the example of the schedules. So, see here, we are having two transactions T1 and T2, and we have come up with two serial schedules. See here, this schedule 1 and this schedule 2 are the serial schedules. So, two transactions T1 and T2 are participating in these schedules. So what T1 is doing? T1 is transferring amount 50 from account A to account B. What transaction T1 is doing? Transaction T1 is transferring amount 50 from account A to account B. And what this T2 is doing? T2 is transferring 10% of the balance from A to B. So both the transactions are using two accounts A and B. Transaction T1 is simply transferring amount 50 from A to B, and what transaction T2 is doing? Transaction T2 is transferring 10% of the balance from A to B. So if these transactions are executed serially, then we may come up with the serial schedules. Right? So see here, we are having this schedule 1, which is serial schedule, and this schedule 2, which is also serial schedule. So in schedule 1, what is happening? T1 is first executing and then T2 is executing. So the sequence is T1 gets executed first and then T2. Whereas in schedule 2, T2 gets executed first and then T1. Right? So both the schedules are valid. Those are serial schedules. So T1 gets executed first and then T2. In schedule 2, T2 gets executed first and then T1. So let us see now the execution of schedule 1 and schedule 2. Both are serial schedules and both are valid. Right? So let us assume that account A, initial balance of account A is 1000. Right? And initial balance of account B is say 2000. So account A is having initial balance as 1000 and account B is having initial balance as say 2000. So if my transaction T1 is reading A, that means it is reading 1000, then it is deducting 50 from A and writing it back to A. So it is writing 950. Okay. Now my transaction T1 is reading B's balance. So B's balance is 2000. So 50 gets added. Transaction T1 is transferring 50 from A to B. So A gets decremented and B gets incremented. So B's balance gets incremented by 50. Right? And finally T1 is writing the balance 2050. Is that correct? So at the end, A's balance would be 950 after executing this transaction T1. A's balance would be 950 and B's balance would be 2050. Okay. Now, the transaction T2 starts after T1 completes because this is serial execution. Okay. So T2 is reading A's balance. So what is being read here? Yes. What is being read here? Yes. What T2 is reading? What is the balance of A that is seen by T2? Please pick up. T1 has successfully completed and now T2 is started its execution. So what is being read by this T2 as A's balance? Yes, please pick up.
950.
Yes, correct. So T2 is reading now A's balance as 950. Now what T2 is doing? T2 is transferring 10% of the amount of A to B. So it needs to compute 10% of 950. So we are having here defined one temporary variable. So A into 0.1. So 10% of A is being computed and that is being stored in this temp. So obviously 10% of 950 is 95 and now that balance is being transferred from A to B. So 95 will be deducted from A and obviously the transaction T2 is now writing this balance 855 to A's account. Right? Now, this transaction T2 is reading balance of B. So what this transaction T2 will read? Balance of B. So that was written by T1. So read B will read 2050. So this same amount 95, right, is being added into B's account because we are transferring it from A to B, right? So 95 is being incremented in B's account. So finally, write B statement will write 2145 in B's account. So this is how this serial execution will produce the results, right? Now, this is a valid serial schedule. This schedule number 2 is also valid, wherein the sequence of execution of transactions is different. So T2 is executing first and then T1. So once again, if my initial balance of A is 1000, then T2 is reading 1000. Now T2 is computing 10% of 1000. So it comes out to be 100, right? So 100 will be transferred now from A to B. So T2 is writing A as 900. So 100 gets deducted from A's balance. So T2 is writing the amount A as 900. Now T2 is reading B's initial balance, so it is 2000. So 100 gets added into 2000. So transaction T2 is writing B's amount as 2100. Okay, now T2 has completed successfully and now T1 comes in. So T1 is reading A's balance. So A's balance that is read by T1 is now 900. So 50 is being transferred from A to B. So obviously A gets deducted by 50. So A will write 850 into A's account. Read B will read 2100 and 50 gets added into 2100. So ultimately the balance would be 2150 after executing this schedule number 2. So see here, this is also a valid schedule, serial schedule, and this is also a valid schedule, that is serial schedule. Both are valid, so both are generating the consistent state of the database. And why I am saying this? Because see here, before executing this transaction, the summation of A and B was 3000. After executing this transaction, the summation of A and B is 3000. Correct? Now, before execution of this transaction, the summation of A and B is 3000. After execution of this transaction, once again, the summation of A and B is 3000. Right? So obviously, before this schedule, the consistency requirement that A plus B is 3000 is maintained. Right? And this is producing the consistent state of database. And similar is the case for schedule 2. Even though the sequence of execution is different, I'll be having the consistent state of database. So both of these schedules are valid schedules and those are known as serial schedules. Right? Now, let us proceed with one more schedule, and that is the concurrent schedule. Right? So, see this schedule number 3. So this schedule is not the serial schedule. Right? This schedule is not the serial schedule, but it is the concurrent schedule. And why we are saying that this is a concurrent schedule? Because few of the instructions from T1 are executed, then few of the instructions from T2 are executed, then once again few instructions from T1, and once again few instructions from T2 are being executed. So this is schedule number 3 is concurrent schedule. Right? Now, if we look at this concurrent schedule and if we go on using the balances and performing the operations, let us see what happens. So in schedule number 3, transaction T1 comes in and reads the initial balance, that is 1000, then deducts 50 from it and writes the balance back to the database. So 950 is written onto the database. Now, what is happening? T2 comes in. So T2 is now reading A's balance. So that is 950 now. So 10% of 950 comes out to be 95. So that is being transferred to B's account. So transaction T2 is writing now the amount 855 to A's account after deducting this 10%, that is 95. Okay, now once again T1 starts executing. So T1 is reading B's balance for the first time. So it is 2000. Now the 50 gets added into B's account, right? So 2050 will be written back in B's account. Now the remaining instructions from T2. So T2 is now reading B. So it is reading 2050. Then whatever was computed by T2 temp 95, it was computed by T2 and it has been stored in some temporary variable. So that amount temp is being added into B's account, and finally T2 is writing the B's amount. Right? So this is the concurrent execution of transactions. So this schedule is having the interleaving of the instructions from T1 and T2. Right? But if you observe, this schedule is having the same order of instructions with respect to individual transaction. So order of instructions with respect to individual transaction T1 and T2 is not changed. Only thing is some instructions from T1, then some instructions from T2, then once again T1, once again T2. So this is a concurrent execution. And if we look at the ultimate result of this schedule, then what we find ultimately, what has been written, the final value of A, the final value of A is written by this T2 and that is 855. The final value of B that is written by once again T2 is 2145. So before execution of this schedule, my A plus B was 3000. After execution of this schedule, once again, the final balance of A plus final balance of B, once again, it comes out to be 3000. Do you agree with me? Yes? Do you agree with me?
Yes, ma'am.
Right.
Yes.
So, this schedule 3 is preserving consistency of our database. And see here, this schedule 3, which is producing A's balance as 855 and B's balance as 2145, this result is same as that of the serial schedule serial schedule 1. So see here, this serial schedule is also producing 855 and 2145. Right? So the same result is being produced by my concurrent execution, that is schedule 3. Right? So in both these schedules, schedule 1 and schedule 3, the sum A plus B is preserved. So even though schedule 3 is my concurrent schedule, it is producing the result which is same as one of the serial schedules. I'll repeat, please understand this concept. Schedule 3 is the concurrent schedule But whatever is the result produced by this concurrent schedule is same as that of one of the serial schedules. Right? And we say that serial schedules always maintain the consistency of the database. So, ultimately, our scheduler should produce the schedules. Those are concurrent in nature, but those should produce the result which is similar to that of the serial schedules. And if such a schedule I am able to create, then that schedule is acceptable by the database system. And such kinds of schedules are producing always the consistent or maintaining the consistency of the database. Right? But if the scheduler is producing the schedule like this, see this schedule, schedule number 4. So once again, this is the concurrent schedule. Once again, the order of individual instructions in the individual transaction is maintained, right? And there is interleaving of the instructions from T1 and T2. But if we look at this particular schedule and if we go with the computation of the results, what is happening here? See here, what is the ultimate value that is being produced by this schedule? For A, it is 950 and for B, it is 2100. So A plus B, if I compute, then it is 950 plus 2100. Right? So this is not equal to my consistency criteria. This is not equal to 3000. Correct? No? So even though this schedule is being generated, this schedule cannot be accepted. Why? Because this schedule is not actually preserving the consistency condition. So the summation of A plus B before the schedule and after the schedule is not being maintained. Right? And that is why even though this also is one of the concurrent schedules that can be produced by the scheduler, such kind of a schedule is not being accepted because it is not preserving the consistency condition. Right? So our scheduler should produce the schedules such that my database consistency is preserved. And here we come up with the concept of serializability. So please write down this definition of serializability. Let us see now the definition of serializability. You please take down this definition. Okay. So, to find non-serial or concurrent schedules that allow transactions to execute concurrently without interfering with one another and thereby producing a database state that could be produced by a serial execution. I'll repeat. What is serializability? Serializability is the concept that will help us to find non-serial or concurrent schedules that allow transactions to execute concurrently without interfering with one another and thereby producing a database state that could be produced by a serial execution. Are you getting me? So in our example, we have seen schedule 1 and we have seen schedule 3. So schedule 1 was the serial schedule and schedule 3 was the non-serial schedule or the concurrent schedule. Right? So what we mean by serializability? Serializability means to find the non-serial or concurrent schedules. So, to find the non-serial or concurrent schedule that allow transactions to execute concurrently without interfering with one another and thereby producing a database state that could be produced by a serial execution. Right? So we may say that this schedule 3 that we have seen, which was the concurrent schedule, right? Wherein we were having the interleaving of instructions from T1 and T2. But the result that this schedule 3 produced was similar to that of the serial schedule. That is schedule number 1. Right? So here we may say that this schedule 3 is following the concept of serializability. What we mean by serializability? Once again, I am repeating, to find concurrent schedules that allow transactions to execute concurrently without interfering with one another and thereby producing a database state that could be produced by a serial execution. So in schedule 1 and schedule 3, schedule 1 was serial schedule, schedule 3 was concurrent schedule, and we have seen that both schedule 1 and schedule 3 were producing the same results. Right? And that is why we are saying that schedule 3 is, even though it is concurrent schedule, it is following this concept of serializability because it is producing the result that is same as one of the serial executions.
Yes, ma'am.
Right. So let us proceed now with the basic assumption that we are having. So here our basic assumption is each transaction preserves database consistency. So obviously the transactions are written by the application programmer. Right? And the application programmer makes sure that every transaction is preserving the consistency of the database. Right? So our basic assumption is each transaction, each individual transaction preserves the database consistency. Right? So this is the very basic assumption. So if every transaction is preserving the database consistency, then obviously the serial execution of set of transactions must preserve the database consistency. Do you agree with me? Yes?
Yes, ma'am.
So every transaction is preserving database consistency. So if I'm having serial execution, of the set of transactions, then obviously my database consistency should be maintained. Right? So that is our basic assumption. So a schedule is serializable if it is equivalent to a serial schedule. I'll repeat what I'm saying. A schedule, possibly it is a concurrent schedule. So a concurrent schedule is serializable if it is equivalent to a serial schedule. Right? So if I am having a concurrent schedule and if the concurrent schedule is equivalent to a serial schedule, then I'll say that this concurrent schedule is serializable. Right? So we are having different forms of schedule equivalence. Right? And these forms are, we are having the notions of the conflict serializability and the view serializability. So in this course, we are not going to talk about view serializability, but we'll be focusing upon this concept of conflict serializability. Right? And in today's session, we are going to cover this conflict serializability and then we are going to conclude our session. Right? So, let us proceed with conflict serializability. So, henceforth, while going for the concept of serializability, we are going to simplify the way how we are going to write our schedules. So earlier we wrote our schedules like this. So read A, then the operation that actually is being performed by this transaction and then the write operation. Right? But actually we are more concerned about the read and write operations because these read and write operations are actually affecting the consistency requirements, right? And that is why henceforth we are going to simplify our schedules, the way how we write the schedules. And now instead of having all such kinds of operations in the schedule, we are simply ignoring these operations wherein we are computing something. And we are only having now the read and write operations belonging to the respective transactions. So henceforth our schedules will involve only read and write operations. Right? Now let us proceed with the concept of conflict serializability. So let us consider that we are having a schedule S, wherein we are having two transactions, those are participating. So in my schedule S, I am having two transactions, those are participating. And these transactions are transaction TI and transaction TJ. So what we have? We are having schedule S and two transactions TI and TJ are participating in this schedule. Right? Now, let us assume that we are having two consecutive instructions. Two consecutive instructions in our schedule S. And these two consecutive instructions belong to two different transactions, TI and TJ. So let us denote that TI is the instruction from, II is the instruction from transaction TI and IJ is the instruction from transaction TJ. And these two instructions are consecutive instructions in our schedule. Right? So once again, I am repeating, we are having a schedule S. Two transactions are participating in this schedule S, and these are denoted as TI and TJ, right? And in this schedule, I am having several instructions from TI and TJ, and those instructions are being interleaved, right? So this is the instruction from TI, this is instruction from TJ, this is once again the instruction from TJ, this is the instruction from TI, and so on, right? And this is my schedule S. So what we are saying, this schedule S comprises TI and TJ, right? And we are having the instructions II and IJ. Those two instructions are consecutive instructions, and those belong to two different transactions, TI and TJ. So what we mean by that? See, for example, this instruction and this instruction are two consecutive instructions, and those belong to two different transactions. Or this instruction and this instruction, these two are consecutive instructions, but these two belong to two different transactions. So this is my II that belongs to transaction TI, and this is my IJ that belongs to transaction TJ, and these two instructions are consecutive. Okay, now I hope you must have understood this concept. So let us proceed now. These two instructions now, II and IJ of transactions TI and TJ, we say that these two instructions II and IJ conflict with one another if and only if there exists some item Q that is assessed by both II and IJ, and at least one of these instructions is writing this data item Q. What we mean by that? Say for example, if both these instructions II and IJ are accessing the same data element, say Q. So both II and IJ are accessing the same data element Q. Okay, and if one of these instructions II and IJ is writing that item Q, then there is a conflict. What we mean by that? See, for example, if my two consecutive instructions II and IJ are read instructions, so both are reading the data item Q. So there is no write instruction involved. So if both are reading the same data item, then there is no conflict. But if II is reading and IJ is writing the same element Q, or II is writing the element Q and IJ is reading Q, or both are writing the same element Q, then in all these situations, one of the instructions is the write instruction, right? And both are accessing the same data element. Then if this is the case, then we say that these two instructions II and IJ conflict with one another. So once again, I am summarizing. One schedule S, TI and TJ are two transactions. Those are participating in this schedule. II and IJ are two consecutive instructions from the schedule. Those belong to two different transactions, TI and TJ respectively. In this situation, if both II and IJ are accessing the same data element Q, then we may say that there is a conflict if one of the instructions from II and IJ is writing that data element. So in this situation, whenever the sequence is like read Q, write Q, or write Q, read Q, or write Q, write Q, then one of the instructions is write. So all these combinations will produce a conflict. Whereas if both the consecutive instructions from two different transactions are reading the same data item, there is no conflict. Okay, now what next? It is very important. A conflict between II and IJ forces a logical temporal order between them. So if there is a conflict, then the logical order need to be maintained as it is. But if there is no conflict, then what we can do is we can interchange these instructions. So if there is no conflict, then it is possible to interchange the sequence of II and IJ. Right? So let us see one example so that we can understand this concept well. So if initially I am having this schedule S, and if by swapping of non-conflicting instructions, if I am producing another schedule, say S dash, then I'll say that this S and S dash are conflict equivalent. So what I'm doing, I'm having the original schedule S, and if there are the instructions, those are non-conflicting. What I can do, I can swap the sequence of those instructions, right? And I may come up with another schedule that is S dash. Okay, so if I'm swapping the non-conflicting instructions, and if I'm coming up with another schedule, say S dash, then these two schedules, S and S dash, are conflict equivalent. Conflict equivalent. And if we say that schedule S, if we swap the non-conflicting instructions multiple times, and ultimately if we come up with a schedule S dash, which is a serial schedule, then we say that this original schedule S is conflict serializable. So the schedule S is conflict serializable if it is conflict equivalent to a serial schedule. So I'm going to explain this concept with the example, and then we'll conclude this session. Okay, so see here, we are having this schedule number 3. So we are having these statements like read A, write A from T1. Then from T2 we are having read A, write A. Okay, from T1 we are having read B, write B. And from T2 we are having read B, write B. So we are having this schedule 3. So what we are going to do is, we are going to look at the consecutive instructions. Consecutive instructions from two different transactions which are non-conflicting. So what we mean by this? So see here, we are having this write A and we are having this read B. See here, this instruction belongs to transaction T2. and the next instruction belongs to transaction T1. So these two are the consecutive instructions. Okay, but these consecutive instructions are not accessing the same element, same data element. This instruction is writing A and this instruction is reading B. So even though these consecutive instructions belong to two different transactions, they are not accessing the same data element. So they do not conflict with one another. When they conflict, if they are accessing the same data element, and if one of the instructions is right, then they conflict, otherwise no. So if we look at these two instructions do not conflict with one another. So what we can do simply is we can swap the order of these instructions. So simply what we are doing is we are shifting this write A downwards and we are moving this read B upwards. Right? So simply we are swapping these two instructions. So read B will go up and this write A will go down. Okay, now this is another schedule that we have come up with. So we may say that this schedule is conflict equivalent to this schedule number 3. This schedule is conflict equivalent to this schedule number 3. Now, let us see further. So if I look at this and this, these two instructions, once again, these two instructions are consecutive instructions. One belong to T1, one belong to T2, and both are accessing different data elements. So once again, there is no conflict. So once again, what I can do is I can swap these two. Right? So after swapping these two instructions, what will happen? This read B will go up and this read A will go down. So I am having one more schedule which is equivalent to this schedule number 3. So this schedule is also conflict equivalent with schedule 3. This also is conflict equivalent to schedule number 3. Okay, now once again, if we look at this particular schedule, what we find is this write B and this write A. These two are consecutive instructions, and even though these are the right instructions, they are accessing different data element. One is accessing A and another is accessing B. So once again, here also these two instructions do not conflict with one another and we can swap those. So once again, after swapping these two, this will go up and this will go down. So we'll be having this schedule, right? So once again, if we look at this particular read A and write B, right? Once again, these two are the consecutive instructions from two different transactions and these do not conflict with one another. So if they are not conflicting with one another, once again, what we can do is we can swap these two. And if we are swapping these two, we come up with this schedule. And if you look at this schedule 1, this schedule is the serial schedule. Right? So what we have done, we have this schedule 3. We have found out the instructions, consecutive instructions, those are not conflicting with one another. And if they are not conflicting, simply we are swapping the order of these instructions. So if we are having such kind of series of swaps, and if we are coming up with a schedule which is serial schedule, then what we can say here? We say here that schedule 3 is serializable, or more precisely, we may say that schedule 3 is conflict serializable. Why? Because it is possible to come up with a serial schedule by swapping non-conflicting instructions. Right? So, the same thing we have written here. Schedule 3 can be transformed into schedule 1, which is a serial schedule where we are executing T1 first and then T2. Right? And we have come up with this schedule 1 by a series of swaps of non-conflicting instructions. So here, if this is the case, then we say that this schedule 3 is conflict serializable. So any doubt?
Ma'am, will you repeat this?
Yes. So what we did, we had this schedule number 3, right? So what we did, we are having the interleaving of the instructions from 2 different transactions. Right? Now, what we are trying to do, we are trying to find out whether this schedule that is being produced by my scheduler is serializable. So what we mean by serializability, we have gone through the definition of serializability, right? So if I'm having a non-serial schedule or a concurrent schedule like this, schedule number 3, it is a concurrent schedule. And if this schedule is producing the result which is similar to that of the serial schedule, then we say that this schedule is following the concept of serializability. So simply, we are talking about one such notion of serializability, and that is known as conflict serializability. So what we do in conflict serializability, given a schedule, we check whether this schedule is conflict serializable. If this schedule that is being produced by a scheduler is conflict serializable, then that kind of a schedule can be accepted. Why? Because it is producing the result which is similar to that of a serial schedule. Right? Now, how to test it whether this schedule is conflict serializable or not? We are having some rules. So what are those rules? I need to find out the consecutive instructions. Those belong to 2 different transactions. So if these 2 transactions are non-conflicting instructions, then it is possible to change the order of these 2 instructions. So what are non-conflicting instructions? If 2 consecutive instructions are accessing different data items like this, then definitely these are non-conflicting instructions, irrespective of whether it is a write operation or the read operation. So very first situation is if instruction II and instruction IJ are accessing different data items, then definitely they do not conflict. they do not conflict. And if they do not conflict, then we can change the order of these instructions. So simply we are doing the same thing. So we are having here write A that belongs to T2 and read B that belongs to T1. So these two are accessing two different data items A and B. So these two do not conflict. So we are swapping. Sorry. So what does this mean, swapping? So we are changing the sequence. So read B will go up and write A will go down. So swap. Swapping the order. Right? So read B will be executed first and then write A. It is allowed because they are non-conflicting. Now we come up with this schedule. So in this schedule, we are having once again two instructions, read A and read B. Once again, these two are accessing different data items, and that is why they do not conflict with one another. So once again, we can swap these two, meaning read B can be executed first and then read A. So we are changing the order. Right? Now, we come up with this schedule. Once again, we find that there are these two instructions, write A and write B, which once again do not conflict with one another. Why? Because the data item is different. So once again, we may change the sequence. So write B will be executed first and then write A. Okay? So we come up with this equivalent schedule. So once again, if we look at this write B and read A, then once again these two are not accessing the same element. So once again, we may swap. They do not conflict with one another. So we may swap. So after swapping these two instructions, we come up with this particular schedule. So this is my schedule number 1. So if we look at this schedule 1, then this schedule 1 is conflict equivalent to this schedule number 3. Okay, and also this schedule 1 is the serial schedule. So if it happens that after swapping the series of non-conflicting instructions, if we come up with a schedule which is serial schedule, then we may say that this schedule 3 is conflict serializable schedule. Right? So I hope you must have understood now what we mean by conflict serializable schedule and what is conflict serializability. So obviously, if we come up with this kind of a serial schedule, then output of this schedule and output of this schedule are same. Right? So schedule 3, if we execute it as it is, it will produce the output which is similar to that of the serial schedule, that is schedule 1. And that is why such kind of conflict serializable schedule can be accepted by our system. So this is allowed. Right? So I hope you must have understood now. Any doubt?
No, ma'am.
Fine. So see here, this is one more schedule, and this schedule is not conflict serializable. So why we are saying it is not conflict serializable? See here, T3 is having read queue and write queue. So these two are consecutive instructions. Both are accessing the same data element. So these two conflict with one another. Right? And that is why it is not possible to swap. Also, if we look at these two are also conflicting with one another. So we cannot swap. So we are not able to swap the instructions in this schedule to obtain the serial schedule either T3, T4 or T4, T3. So it is not possible to come up with the serial execution like T3, T4 or T4, T3 because it is not possible to swap these instructions because those are conflicting, right? And that is why we are saying that this schedule is not conflict serializable. Got it? Yes?
Yes, ma'am.
Fine. So this was related to conflict serializability and we have gone through the example as well. So I hope you must have understood this concept. So we are going to conclude this session today and we'll see you tomorrow with the new concept, right? So let's conclude and thank you.